Now let's just move on further towards the question number 3, which says in the figure, so we have this figure, DE is parallel to OQ. It says DE is actually parallel to OQ, and EF, as you can see over here, this particular line DE is parallel to OQ, and further we have the given information as DF. This particular line is actually parallel to this line, that is OR. So in the question, DE is parallel to OQ, DF is parallel to OR, and then we have to show that this EF is actually parallel to this QR. So let's just show this thing that EF is nothing but parallel to QR. So first of all, we'll start with the very first information that is given to us in the question. So let us suppose if I'm writing out the solution of this one by taking the given statement first. So as it is given to us, as it is already given to us that DE is parallel to OQ. So if DE is parallel to OQ, then we can say that in the triangle POQ. Let's just see the triangle POQ. As you can see, POQ is nothing but this triangle, and in this triangle POQ, we can see that this DE is actually parallel to this OQ. So if in a triangle POQ, DE is parallel to OQ, if in this triangle DE is parallel to OQ, then by using the basic proportionality theorem, that if a particular line is parallel to the third side of a triangle and dividing the other two particular sides in the two distinct points, then it divides them in the same ratio. It implies that DE divided by EQ is equal to PD divided by DO. So as you can see over here, if we are talking about this particular triangle, then we can see this PE divided by EQ is equal to PD divided by DO. So this is not DE, this is PE divided by EQ, which is equal to PD divided by DO. Let us suppose if I am calling this as equation number 1. Now let's just move on further towards the other condition. So in the other condition, let us suppose if I am talking about in the triangle POR. So as you can see, we have the triangle POR. We are taking this triangle. So in this triangle, it is already given to us that DF is parallel to OR. This condition is given to us. So again, we can say by using the basic proportionality theorem, by using the BPT, if we have this particular line parallel to this line, it implies that their corresponding ratios are equal, means PD by DO is nothing but is equal to PF by FR. PF by FR. So let us suppose if I am taking it as equation number 2. Now you can see from the equation number 1 and from the equation number 2, a very important condition we are getting, that from equation number 1 and 2, we are getting a statement as PE by EQ is equal to PD by DO, which is again equal to PF by FR. So if we have these three ratios equal to each other, it implies that PE by EQ is nothing but is equal to PF by FR. So we are talking about the ratio of all these sides. As you can see, we have PF by EQ is equal to PF by FR. So PE by EQ is equal to PF by FR. So this statement, or we can say this condition, actually reminds us the converse of the basic proportionality theorem, that if the ratios are equal to each other, it implies that this line should be parallel to this one. This is all about the converse of BPT. So hence, by using the converse of BPT, by using the converse of BPT, we can say from this particular statement that EF is actually parallel to QR. EF is actually parallel to QR by using the converse of BPT. So hence, this is the thing that we wanted to prove or wanted to show. So hence, proved that EF is actually parallel to QR. So using the basic proportionality theorem and using the converse of the basic proportionality theorem, we have proved that EF is actually parallel to QR. So this is all about the question number 3.